Okay, when we left off last time, we were talking about different types of bonds. So we used the periodic table to get information about protons and electrons and draw these electron configurations for different elements, and then determine whether those atoms would be reactive and want to interact with each other. When we're drawing out chemical formulas after we have these things that have interacted with each other, we use some basic conventions. If we have a single line between the symbols of the elements, then that represents a bond, which is representing the sharing of a pair of electrons. If we use a double line, then we're sharing two pairs. It's a double bond. So you may see that as we start moving on into some of the other organic chemistry aspects of the semester. Now I want to talk about one thing that we missed before, which is talking about what an isotope is. Now, an isotope is an atom of the same element with different numbers of neutrons. So remember, the number of protons can never change. That's determined by that element, and that is shown with the atomic number. The number of electrons can change because we can gain or lose electrons. But the number of neutrons can also change. And what that means is I can end up getting an atom that is heavier than other atoms of the same element. So what that means is I can end up with a radioactive, or this should actually say unstable, atom. So an example of that would be iodine 131. Iodine 131 is heavier than iodine 127, which is the mass or the mass number that you see on the periodic table. So this one has 4 extra neutrons. What that means is that this isotope of iodine wants to deteriorate back into this lighter one that's more stable. If I have a really unstable atom, then we can give off radioactive particles during this deterioration. Now, where that can be useful medically is, let's say I want to look at somebody's thyroid. The thyroid is soft tissue, so it's not going to show up really on an X-ray because X-rays typically show denser material. But the thyroid uses iodine to make its metabolic hormones. So I can give a patient radioactive iodine. The thyroid is going to grab that iodine out of the bloodstream and use it to make the hormones. And in the process, my thyroid is now going to light up like a Christmas tree on an X-ray. So it can be useful to help me to show soft tissues that would not normally show up on X-ray. Carbon is another good example where we can have different isotopes of carbon, and these heavier ones want to deteriorate back. You may have heard of something called carbon dating, which we're not going to really get into in this class, but it's in reference to that, using the deterioration of these isotopes of carbon. That helps us to determine the age of something. All right, the last time we talked about bonds, so we had non-polar covalent bonds. Remember, polar means a difference, so there's no difference. So these would be atoms that are identical, sharing a pair of electrons equally. A polar covalent bond, then, remember, is where you have maybe a bigger atom and a smaller atom sharing a pair of electrons. So the electrons get hogged by the larger atom. So we have unequal or polar sharing between those atoms. We also had ionic attractions, where you had one atom that got rid of his extra electron. That electron got grabbed by somebody else who needed one, and you ended up with something with a positive charge and something then with a negative charge. And then those opposite charges are going to be attracted to each other. So we see this typically in salts. Let's take a look a little bit further at a really important polar molecule, water. So water is important because we have this big oxygen and these little hydrogens. And that big oxygen ends up hogging the electrons, so he's a little bit negative. And your hydrogens are a little bit positive. What that means is then you end up getting water molecules that are going to be attracted to each other by weak hydrogen bonds. Those hydrogen bonds or hydrogen attractions that we're seeing here between the water molecules are going to give water a lot of really important properties, and you'll see more about that in one of the other videos. We also use hydrogen bonds to hold together the two halves of DNA. Because they're very weak bonds, it's really easy then for us to split that DNA apart when we're dividing it and copying it for cell division. Let's talk a little bit about water and pH. So pH is really a measure of the hydrogen ion concentration in a solution. So if we have something that's a neutral pH, we're going to have hydrogen ions and hydroxide ions in equal numbers. And that's going to give us something of a pH about 7. If we look at human blood has a range of 7.35 to 7.45, and that's a really important range. Make sure that you know that. So if my blood ends up higher than 7.45, then it is too alkaline. So we say that you're going into alkalosis if you're greater than 7.45. If your blood is less than 7.35, it is too acidic, so we say that you are going into acidosis. And those two conditions can start to denature proteins that are important in body functions, and then different parts of the body, different systems start to shut down. Let's look a little bit at the pH scale. So if I'm neutral, then my hydrogen ion concentration is going to equal my hydroxide ion concentration. As I go towards acidity, I'm going to have more hydrogen ions and fewer hydroxide ions. The opposite is going to happen as I move towards a base. So as I go this way, I'm going to have fewer hydrogen ions and more hydroxide ions. Remember, blood is going to be running right about in here. So 7.35 to 7.45. It's important that you stay there. You don't want to neutralize your blood because a pH of 7 would be lethal for you. Now, it's important, as I said, to stay within that very narrow 7.35 to 7.45 range. And so in your blood, you have important substances that are going to help us maintain that range, and we call these buffers. So a buffer is something that really doesn't want to change pH. So my triangle just represents change. So the buffer doesn't want to change pH. So you have buffers in your blood that want to stay in this range. And if you throw hydrogen ions at them, that would normally start to make you become more acidic. Your pH starts to drop. And these buffers are able to grab those hydrogen ions and bind them up. If I go above 7.45 and my body's giving off hydroxide ions, then those, that's a negative, then those buffers are able to grab those hydroxide ions and bind them up as well to keep within that 7.35 to 7.45 pH range. And that's very important for body functions. Not every part of your body does best in that range. If we look back at the pH scale, your stomach acid here is going to be closer to a pH of 2. So the enzymes that are going to be found in your stomach are going to do best at a very, very low pH, around maybe 2 to 3. Whereas enzymes that are found in the rest of our body are going to do better in the same pH range as blood. Now there are some very important buffer systems in the bloodstream or in the body. We have protein buffer systems. We have phosphate buffer systems. So protein buffer systems, phosphate buffer systems, and this really important bicarbonate buffer system. Now this might seem a little confusing with this equation, but if we just look at it, we mentioned before that carbon dioxide becomes carbonic acid in the bloodstream. And the reason for this is as the CO2 goes up, think of it as making everything go downhill down the slide, which means we're going to slide this direction in our equation and give off a bunch of hydrogen ions, which is going to make us go into acidosis. Now, if I can get rid of these hydrogen ions, or if I can blow off the CO2 so my CO2 levels drop, then my equation tips back this direction and those hydrogen ions get bound back up, so I'm not as acidic. So breathing out CO2 is really important for helping us to regulate this pH in our bloodstream. If we look at blood compared to water, if I take something like blood and I start, so that's my dark line here, and I start adding hydrochloric acid to it, notice this pH of the blood does very gradually decrease. It becomes more acidic, but very, very slowly. I always think of it as going kicking and screaming. But if I take water, which is the light gray line, and I add hydrochloric acid to it, look at what happens to the pH. Boom. It goes down almost to a pH of hydrochloric acid almost immediately. So that means that blood is an excellent buffer, or I should say the substances in blood are excellent buffers, whereas water is a terrible buffer on its own. All right, so that gives you a quick overview of some of the other chemistry that we've done, as well as pH and buffers.